Christoph Lameter. He was working as a lead in research and development for an algorithmic trading company in Chicago until the end of 2018, and is currently maintains the slab allocators and the per CPU subsystem in Linux kernel. He's contributed to a number of Linux projects since early 90s. He, as a kernel developer at SGI, he helped pioneer the use of Linux for supercomputing and developed the necessary kernel capabilities for HPC. Recently, Christoph took a new job at, I'm going to butcher this name, but I will try, Deutsche Boerse, to help with their technological challenges and future technological direction. So Christoph, please help me correct if I pronounce the company name wrong.
Okay, the company name is the Deutsche Boerse. And the Deutsche Boerse is the company that operates the European Stock Exchange and various other stock exchanges in Europe. It is the largest stock exchange in Europe, I think, and pretty important for the overall economy. And it's running Infiniband.
Oh, interesting. Okay, thank you for that. Yeah, thank you for the introduction. I tried to look it up how to pronounce, but it wasn't an easy one. Please go ahead.
Yeah, how do I change slides?
Just say next slide, please.
Okay. Okay, next slide. Okay, so I'm talking about the trading system. Though the trading system is extensively documented on the website of the Deutsche Boerse, and I can only talk about what I've done in my lab. Nothing that I'm saying here should reflect on anything that's going on right now with the real working system. And if anybody wants details on that one, they should look at the websites and not to my talk for any details and any way how they're going to interact with the trading system. So I just want to make sure that the production system is out of bounds here. This is research we've done in a lab with a T7 app to investigate certain things. Next slide. So as I said before, the T7 trading engine is based on Infiniband technology, and it has been running for almost a decade now, driving the stock exchanges in Europe. It's not only in use at the Deutsche Boerse, but also in other trading venues, and it has been spreading all over, and it's been growing for years now. Next slide. So the multiple aspects of T7. Most of the customers connect through to the trading system using Ethernet. And so that is used because it's in common use and easy for the customers to use. And that high-speed fabric is very low latency and very deterministic. Once it reaches the T7 core system, the communication between those nodes in the T7 system is using an Infiniband and RDMA. So on the 10 gig infrastructure, we have an intense competition for low latency trading, and there's a fight there over nanoseconds who can be faster than the other to reach the be able to compete and get the best trades after a market event happens. The T7 system uses middleware to isolate the application from the details of the RDMA stack. There's a company called Confinity Solutions that provides a messaging stack called low latency messaging, which was initially developed by IBM, but these days it is maintained by another company that's also sitting close to the Deutsche Boerse in Frankfurt here. And so the application developers has this library where they can have a nice abstraction layer from the details of the RDMA layer. Next slide. So now a short overview over the interface for the customers. This is first of all, the Ethernet portion. On the very right-hand side, you have the Infiniband portion. The participant has a way to submit orders to the stock exchange. Maybe you want to buy or sell stocks. And then there's an outflow where the market data comes out. So the current value of symbols changes to the value of various instruments and stuff like that. And what typically happens is that customers decide based on changes to the value of stock if they want to buy or sell one of these stocks. And the decision-making process must be very, very fast in order to be able to actually get that stock, because there are a lot of different companies all having the same arrangements, and they're all competing to make the best trades here. So the participant is highly motivated usually to reduce the latency, and that's where the things get optimized down to the nanosecond level. In the access network, the data is concentrated for the T7 system when the orders coming in, and when it comes out, there's a fan out. And on the next slide, we're going to have the fan in and the fan out. So now we have spread this out. So the participant submits an order via various switch layers. It gets concentrated. It goes into the T7 core, where it is going then to a matching engine, which matches the buyers and the sellers. And then these events get reported out back to the market data network, where the participant can see what happened, and other participants also can see what happens. And these events may affect the value of a certain stock, and thereupon new orders come into the market. That is a basic working of the trading system. Next slide. Now let's go into the Infiniband stuff, the RDMA stack. This is the basic layout of a single node in the T7 app. It's pretty standard. There's two HCAs that interface to basically two different fabrics. The HCAs are handled by the RDMA layer, and on top of the RDMA layer, you have the various apps running that all use the Confinity messaging layer to interface with the RDMA layer. The reason that there are two fabrics is to have a certain failover. If one of the HCA fails, then the traffic can be routed via the other ones. And the two fabrics have distinct roles. The data fabric contains the really important production data, and the monitoring fabric contains the data where you analyze what's going on with the data, and where you can actually explore how long certain things take and what happened there. And that's actually very important, because customers often demand that investigations occur when something doesn't work according to their liking and they did not get a certain trade. But both fabrics have a lot of headroom, so that it is possible to reroute the traffic over the other one if there should be an issue there. The hardware has been very stable and has been using Intel CPUs and PCIe 3 for the longest time. One thing to notice is that multiple instances of CLLM operate on one machine. So if you have multiple apps, they all have their own messaging layer, and they all do their own interfacing with the Infiniband stack. So this is a multi-threaded environment that is not designed according to low latency standards like what the customers are doing. And so their queue pairs are data from queue pairs is processed in this by these apps, but sometimes these apps can be scheduled out for milliseconds. So there is a potential that messages can get lost and that queue pairs can be overrun. And this is compensated for by the messaging layer, which will then do retransmits and make sure that data is showing up reliably between the apps, that the communication is reliable. Then we have an additional element here, an IBACM, that we have used a couple of times, and that is basically a caching layer. The problem now is that each of these RDMA apps does their own resolution. And so it can happen that multiple of these apps ask the network layer for the same data. And so there are now requests for the same data from the same machine going out and causing unnecessary traffic. So there's a cache that we can put in there that will intercept the request to the subnet manager for data address resolution and provide information to multiple apps that may all be asking for the same information, and therefore it reduces the traffic on the fabric. Next one. Then this is a view of the overall design of the T7 system. It is basically designed to be redundant. There are two different sides to this thing that are in separate locations that are separate, so that if something happens on one side gets destroyed, the other one can continue trading. And so both the data network and the monitoring is in both locations, and hosts on both locations are connected to the infrastructure here. And so the intent here is to have no single point of failure. The middleware, the Confinity low latency messaging, also provides the ability to have redundant services. It can monitor services on multiple hosts and make sure that there's a failover occurring if one of these services fail. So if one host, let's say host AB, fails, then this service can be taken over by some other host automatically, and the system can continue without a problem. So we already said that one side can completely fail and the other side will continue, will take over all the services, and there's enough headroom for that. What can also happen is that one of these fabrics, the data or the monitoring fabric, can completely fail and the other one can completely take over. So there's redundancy both physically as well as fabric-wise in this setup. And we also have redundancy in terms of the services running on individual hosts that can have failover to another host. So this is a very resilient system, and that was deemed to be important because of the importance of the stock exchange for the economy. Yeah, this also means, okay, any link can also fail. So if a link fails, then also a service may be impacted, and so then DSM will route around it, and the failover logic of the various services will make sure that this is worked around. Next slide.
Christoph, there are a couple of questions. Do you want to take it now or wait till the end?
Yeah, I can take it now. Both sides are in the same IB subnet, yes. It's this one subnet that gets basically labeled differently, but it's really the same subnet.
Okay. You mentioned that the failover to the second fabric is possible. However, it would require extra effort to set this up, right? Could you tell more about the general outages you have seen in the environment?
Oh, this is fully automated. So this basically, there are two subnet managers, one in each of the sides, and if one side fails, the other one will take over, and it's fully transparent and fully automated.
Okay, all right. In the cache line layer, do you need to worry about the cache data ever getting out of date?
There are certain measures you can take to probably keep that mapping between the lids and the GUID stable. And if you do that, you can you don't never have a change there, and then it works.
Okay. Are both sides in the same IB net?
Yes.
Okay. Then there's one more question. Is the implementation of failover techniques covered by RDMA layer via UCX, for instance, or is there a unique implementation of the failover capability?
The failover is partially done by the Infiniband design, like the subnet manager can fail over. The other elements come with a middleware, which has a failover logic as well, and ensures that multiple processes can run concurrently, and it can verify that both processes perform the behave the same way, and can kick one out if one misbehaves. So there's redundancy both by the IB fabric as well as by the middleware layer. And there are more things also done even on the application layer to make sure that this is all redundant.
Thank you. Mark, you raised your hand. Did you have a question? Mark Babbage. Okay, guess not. Okay, thank you. This is it for now. We'll take a few questions at the end.
Next slide. Okay. So now we're talking about multicast. So the problem here is that there's a lot of events being spread across the fabric into the customers and stuff coming in and out. And it's very important that events can be replicated without building point-to-point connections. And so what we're using here is multicast. So multicast relies on the switches rapidly copying and replicating data. And so this is done by the switches in the IB fabric. The sender can send one message and it reaches all subscribers. Also, this could be going out to hundreds of nodes in the fabric as well as to 10,000 systems out there on the Ethernet fabrics. So this is a very efficient mechanism that is relied on. This is key to a lot of financial applications like stock exchanges or trading systems. So the overwhelming part of the traffic on the fabric is therefore multicast traffic. The data volume that can be processed on the T7 depends on the effectiveness of the multicast traffic. And so what we've seen while looking at the lab is that CLM implements separate consumer and publisher instances. So the Infiniband fabric has different ways of joining a fabric. It can join the fabric as a reader, as a listener only, or as a sender only. And the problem is that the joins to the multicast fabric was done in such a way that the sender also received all messages. And so we got a new version from the community that implemented the send-only join so that the senders didn't also receive a copy of all the data, and this significantly dropped the traffic in the fabric. And then we also found another bug during failover when one SM becomes breaks and must offer over to the other. We found that there was an issue also with the send-only registration logic, and actually I wrote a patch to fix this, and this was upstreamed recently, and it's now also going to be part of Red Hat 7 and 8. So the high rate of multicast traffic that the T7 application had in the past seems to have led a fallback to unicast connections by the application designers of T7. And so since their volume now is reduced of the multicast, we were able to use multicast again. And with that, we had another reduction in the volume of traffic and the number of the resolutions that go to the subnet manager and all that. So we did some work here to enhance the use of multicast, which significantly affected the effectiveness of the system. And in the meantime, we had to fix various bugs that occurred on various levels. Next slide. Now we're getting to the subnet manager. This one is which the subnet manager manages the routing and the node information on the fabric. It's key to the operation of the fabric. Next slide. And so historically, the Deutsche Boerse has used the OpenSM in Red Hat, and it ran the straight drivers in Red Hat for an extensive period of time, actually for the last 10 years, and there was not a problem at all. But when we tested this in the lab, we saw that there was an unusual high level of SM requests during the start of the app, and also doing experiments with failover. So we were wondering what was going on. And so we saw that during certain times, the subnet managers were saturated with traffic, actually. And so at that point, the backup SM started to fail to see heartbeats. So, we thought maybe we could try to put the heartbeats outside of the fabric. So let's put it on something else like Ethernet or something. But that's not possible with a standard open source SM. And so we were very concerned there that the split brain issues could result because that was not done properly in the open source solution. And after we saw this danger, we found a test program called Osm Test. It's part of the automated diagnostic, and you just try to saturate the fabric with SM requests to see what happens in the worst case scenario. The whole system began to fail, and individuals host started to reboot without discernible cause. And so we thought, okay, from that we can certainly deduce that we have to take care of the SM load and make sure that this is under control and that we monitor the SM carefully. So it seems that the high levels of subnet manager traffic cause high level of drops of the management package, and this can be a serious problem. So then we contacted Mellanox about the issue. And we were told that the SM in Red Hat is no longer maintained, and actually that they did not backport any fixes in the last couple of years. And that was pretty disconcerting, because before, I think they had to be able to rely on Red Hat providing updates. We were then recommended to use Mellanox SM that came with MoFed, but that still didn't have the heartbeat functionality that we wanted. And so we finally ended up with looking at the UFM, the UFM Fabric Manager, that is a new development by Mellanox, which has all these capabilities to configure the heartbeat outside of the fabric and to make sure that overload conditions on the SM do not lead to split brains and all sorts of other things. So that's what we get with the subnet manager. And then the next slide. So then we looked at the middleware, and we saw, as I've mentioned it initially also, that we have some problems here, that every instance of CLLM does its own resolution, and therefore there's no caching. So multiple requests for the single address come from a single system. And we looked at the kernel, and so a surprise, this only occurs for unicast connections. Caching is done by the RDMA subsystem for multicast. So it seemed to be dangerous to use too many unicast connections. And the other thing is with the unicast connection, that these things are retried at regular intervals by the middleware. So if a service on the IB fabric is not up, then we have a continuous stream of SM requests from many services that are trying to contact the endpoint and cannot connect. And so you have a lot of useless traffic going on there. And in particular, if a service crashes that is connected via unicast to multiple other endpoints, let's say a few hundred, then suddenly you get a huge flood of SM requests that will persist until that service is up again. So that is a bit disconcerting. The other thing is, okay, during failover, when one SM takes over from the other, the applications get a re-reg request. This means they need to re-register all their multicast and unicast connections. And at that point, we saw extreme SM load, in particular since the TCM apps had a huge number of unicast connections. And all the connections has to be reestablished. So the level of SM requests, even in a small setting in the lab, get to pretty high to us, and it looked very dangerous. So we thought about, okay, we probably need a cache here, because if the address information would be cached locally, then the address information for one thread can be used by another. And the address information of a node that is no longer servicing a certain thing is also in the cache. So the requests that goes uselessly to the subnet manager also would go away. And we found a cache in the RDMA core package, which was called the IBA ACM cache. And so we looked around a bit and played around with it, and we saw, okay, if we can keep the GUI to lit information stable, then actually we can keep the SM information around for even a day or longer. And there we found that there were provisions in the subnet manager to make sure that this happens. And so others have apparently experimented with this and had the same issues, and the solution was right there. So this is one solution. The other solution is we saw an incomplete implementation of RDMA, RDMA get other info to use the IPOIB cache in the kernel for SM information. That is not complete yet, and actually one could also use the kernel IPOIB stack to cache this information, but we had no time to pursue this further. But it seems to be possible to finish that implementation and then also avoid these issues. So the severity of these re-reg requests led to more talks with Mellanox, and so we try to find ways to avoid the re-registration when the failover occurs. And the registration would not be necessary if one SM would save the state and hand it off to the other one when the failover occurs. Another thing that happens during failover is that the lid changes of the subnet manager, which means that all applications have to change their address information regardless of even unicast and multicast subscriptions. And so we talked with Mellanox a bit and about the engineers that design UFM, and we get a new feature into UFM that's called a static SM lid. And this means that during failover, the subnet manager keeps the same lid. The fabric is being reprogrammed so that the lid now goes to the other subnet manager. And this means that all information can stay stable in an app, and failover does no longer require a re-registration request, and no longer requires the update of the SM lid. And this is actually the best solution. And with that, there should be a very fast failover possible, and all the issues that we saw before could be avoided. Yeah, and still one thing that we still have open with Confinity is this unicast handling of repeated requests to the SM. This is maybe something that still has to be done here. Okay, next. And then, yeah, this is basically what we looked at. And so now a short summary here. Next slide. So how is this resilient? Yeah, the basic T7 philosophy was that any component can fail. And so we have the service failover by CLLM between multiple HCAs. Let's say if you have two HCAs in a system, it can fail over between the two HCAs. It can fail over between the services. Infiniband also implements some failover for critical components like the SM. And the risk in this scenario was because the SM was not evolving with the other components, and this vendor converted it to a proprietary product. The OpenSM used to be open source, and just relying on those updates was no longer working because payment is expected now. That was a bit of a thing that we just were a bit surprised of. And also the Infiniband interface of CLLM was not evolving. The company was focused more on software features instead of the integration with the RDMA system. And so that's probably taken care of now. And another risk arose because the mitigation of one issue, they saw that the multicast data volume was rising significantly and used only unicast instead. And they did not realize that this has consequences that causes increased system load, especially on the systems like the settlement manager, which could cause problems. One of the aspects of failover is also that multicast is a natural way to realize redundancy, because in multicast, you have a network address that's not bound to a single host. So you can have multiple hosts serve the same address. And if one host fails, the other one can still take over. So the multicast that is natural to the financial area is often used for this fact as well. And so the application designers also come up with their own inventive solutions to create redundant services. And one of the unique aspects of the T7 system is a failover by location. So we have separate locations that can fail, but the essential services can continue in a integrated fashion, which is also enabled by all the other resilience services, resilience features that we have or that are there in the T7 app. Next slide. And so some thoughts about the future of the Infiniband at the Deutsche Boerse. Next slide. The problem right now is that when the Infiniband was initially deployed 10 years ago, we had multiple vendors for Infiniband. And today there's just a single vendor, and there's some de-open sourcing going on, which is concerning to us. And it seems that maybe development has slowed down in the last few years. And we are now at speeds that are way higher than would be useful for us. The speeds that we can perform from a PCIe 3 connection in our current systems is probably tops out at 20 to 30 gigabits per second. We can buy hardware that can do 200 or 400 gigabits per second, but that's probably far too much for us. RDMA is really useful, but it makes us out again at QDR speeds because of the overhead that we have because of the processors. We can't really use the higher speeds. And the T7 application is really depending on performance of small packets, not large RDMA data streams. So the RDMA layer is used for messaging, not for real RDMA transfers. So we use the RDMA layer for basically offloading and bypassing the kernel. The RDMA transfers are only used in rare occasions for large data transfers when they occur. So we are now looking at maybe if it would be possible to do the same thing on Ethernet. Problem there is that no consistent offload technology exists on 10 gig. And so the challenge of getting the high throughput from the application to the network is even more complicated because everybody runs their own network stack, bypassing the kernel and stuff. So we are thinking about right now about how to continue the evolution of the system in the next 5 to 10 years. Next slide. And that is all I have to say. Any questions?
Yeah, there are quite a few here in the chat. I'll go through them one by one.
Mm-hmm.
Okay, and please, folks, if you need to add clarity, feel free to open, pipe up here. All right, the question I see is from Donglai. What do different applications represent? Different trading companies?
Different applications can have different services on the fabric. So let's say logging, matching engine, an incoming gateway that mediates connections from a customer into the matching engine, post-processing, compliance checks, risk checks, all sorts of elements.
Okay, thank you. What type of SM requests did you see, or were those SA requests in a stable fabric? It's mostly MCAST activity and some SA queries. So Vladimir, is that? Go ahead, please.
Yeah, so SA requests, SM requests, almost the same, right? But mostly what we saw is path record requests from the unicast connections, and usually we didn't see a lot of MCAST activity because the kernel already caches the MCAST information on each node. And if multiple of these applications join the same multicast groups, there will only be one request to the SM. So we are very happy with the way MCAST worked and how MCAST scales in this fabric. What we were not happy with was the unicast performance.
Okay. All right. Thank you. Sean is asking, what is the size of the system that causes this barely manageable condition in the SM? Does this occur in systems the size of a single rack?
Well, it depends on the amount of unicast connections. You can do. We were able to just have the thing just crash with 10 nodes and just basically running 10 OSM tests concurrently on all sockets and just saturating the fabric with SM traffic. It was just it was unmanageable. And
right.
Actually random reboots occurred because this also exposed a race condition in the RDMA subsystem, which caused a kernel loops, and therefore they started panicking.
Yeah. Sean is going on asking, is Rocky a consideration?
Is what?
Is Rocky a consideration?
Yes. Mm-hmm. We will be exploring other solutions in the future, and one of them is probably Rocky. We have to see if it would do and satisfy our needs. We're looking at various options right now.
Okay, all right. Don is asking, Red Hat is not updating OpenSM because no one is updating OpenSM. OpenSM was primarily updated by Mellanox, who has decided to drop such effort and do it in their MOFED and thus in their switches.
That is exactly correct. Hal Rosenstock, who maintained this OpenSM for 15 to 20 years faithfully, and I knew him, and he was a great guy. He retired 2 years ago, and with that, I think the whole thing stopped. And since then, it's bad.
Okay.
It would be good to have another maintainer for OpenSM that would actively deal with bugs and all the other things. But it seems now that they're only applied by Mellanox to their own version.
Thank you, Christoph. I hear a call to action there.
Yes.
Okay. You were at QDR level 4 years ago. Were there any upgrades to more modern hardware?
We are looking at that right now. So the problem is the Infiniband fabric worked for 10 years and nobody had to worry much about this. So it's time now to do some upgrades, I think. And we'll be looking at that as well.
Okay. Bhamini is saying, amazing overview. Thank you. Is there a potential of leveraging quantum computing for this in the future?
I don't know where this is coming from my doctoral dissertation or what. No, so as far as I can know.
Yeah, okay. Doug is asking, do you see a Rocky SmartNIC as being able to offload any of the work?
Yes, sure.
Okay. How is IB hardware multicast failure handled in case that part of destination set receive in one message and receive duplicated message and retry again?
That's where the Confinity middleware comes in. The Confinity middleware makes sure that the multicast delivery is reliable. basically has a counter in each of the packets, and if an endpoint sees that it misses certain packets, it can ask for a retransmit of certain things. And Continuity LLM then deals with these failure conditions and ensures that all the endpoints get the packets.
Okay. All right. I think that's all the questions we have. Radha is asking if the previous day presentations are available. Yes, they are, including the videos. Please check out our website, openfabrics.org. With that, I'd like to thank Christoph for his time and being here with OFA, taking all these questions. Seems like a very interesting topic for our audience. We hope to see you next year.
All right. Thank you. Bye.